Okay, thank you very much. So this is a sixth session of the part one of a series of lectures in non-stationary time series with modern signal processing techniques. And okay, so this is again the MATLAB code of synchro squeezing, where you can find Dropbox link here or use the QR code. And today's topic will be the basic properties of synchro squeezing. After introducing the algorithms of synchro squeezing, let's take a look at some basic properties of synchro squeezing. And these are some references of Valina or first order synchro squeezing. Synchro squeezing was actually in the very beginning introduced in 1996 as an algorithm, and then we proceeded to study its theoretical foundations, and then there have been several accumulated theoretical developments, and this is just part of it. Okay, the first property I want to discuss is the following. As we mentioned, right now we focus on adaptive harmonic model, and suppose there are multiple components. That is, there are more than one component in the signal. Then we make this assumption, that is, there is a frequency separation. Under this assumption, then we can study how the phase information gives us the instantaneous frequency. And the theorem is the following. The reassignment rule actually will give you the instantaneous frequency, but with some small error when C is very close to the instantaneous frequency, and this closeness can be well quantified. But if you have interest in details, you can go to the paper. And remember, I recall this is the time frequency representation of the respiratory signal, and this is the instantaneous frequency information, how it is hidden inside the time frequency representation, in particular, the short time Fourier transform's phase. And the second one is about how and why synchro squeezing transform can help us to approximate the ideal time frequency representation that we have interest in the very end. So recall this very simple calculation as an example so that we can see what's going on. First, suppose we have a function f, which is a cosine 2 pi cos C0t, which you can write using Euler's formula in this summation of two functions. And then synchro squeezing transform, after doing some calculation, will be this result, where you can see the a is actually the ALT in the ideal time frequency representation formula I gave you. Okay, and this E is the phase, which is here. And then this guy, remember G is an L1 function, so that 1 over alpha G of T over alpha will converge in distribution to delta at 0. So this guy will converge to a delta distribution centered at instantaneous frequency. And there is 1/2, which comes from the real form of the signal. So this gives you that when you have only one component, L, capital L is one component, and it is harmonic, then we can somehow recover the ideal time frequency representation in this sense. When alpha is very, very small. Here is the alpha times the whole of G and so on, and then 0 otherwise. So this is what you can get by playing with very, very simple harmonic function to get an ideal time frequency representation. And this is the picture in general. So in general, the synchro squeezing transform will give you an approximation, and the approximation is in the sense of what I showed you before. That is, this delta will be approximated by 1 over alpha G of something. And this is the picture. This is a signal, 3 components, summation. This is a ground truth, so that this is 3 instantaneous frequencies. So you have, this is ideal time frequency representation, and this is synchro squeezing transform. And now we can use this example to further visualize the benefit of recovering the ideal time frequency representation via squeezing. So let's take a look at this two signal and the summation is this guy. So you can see there are a lot of dynamics, right? The behavior here and there, they are different. And what is its ideal time frequency representation? It looks like here, because this signal is generated by me, so I know the instantaneous frequency, so I can plot them here. And we can further pile on the amplitude modulation and so on, but to save the effort, just to make it simple, I just show you two lines, and that is how the ideal time frequency representation should look like. First frequency, second frequency, and so on. But before looking at the benefit of squeezing, let's take a look of the power spectrum. As we have known, the power spectrum of this kind of signal can be crazy. Now I have told you there are two components with time varying frequency, and this is a power spectrum. And what do you really get? Right? It is very difficult to say what's going on. So for example, if you study a signal using Fourier transform, after getting power spectrum, we want to find peaks. Then what is the peak? Or what is the peaks? What are the peaks? It is difficult to say what's going on in the power spectrum. But if we now jump to time frequency representation, and we take a look at the spectrogram or short time Fourier transform, this is how the time frequency representation looks like. You see, there are two curves which follows very closely to the ideal time frequency representation. But you see there are some kind of small weird thing in the end when two frequencies are close. You see there are some beautiful spatial pattern. White, dark, white, some interference pattern. And this is the phase interference. And now if we pay a closer look, we just focus on this time, 6.1 second. You can see in the frequency axis, you have two peaks. Nice. But if you focus on at least a 15th second, you see, hey, where are two spikes? There should be two, but you only get one. Then this is very difficult to identify or to determine what to do. Also, you may say, hey, look, there is a small spike here, but it's very difficult for me to say too much. Now let's take a look at the first order synchro squeezing or the Ranina synchro squeezing. This is the result you get. As you can see, well, it is much sharper, as you can see. And we encountered some spreading around this region, some spreading. Well, it's kind of a bit annoying, but that's what we mentioned before, why we need to use the phase to consider higher order synchro squeezing. And this is some kind of spreading again. And now we focus at these two times, you see how it's quite nicely separated. And at this moment, in the very end, it's much better separated. At least you can now see two peaks. But, well, because of the phase issue and so on, if we consider further to use the second order synchro squeezing by taking the group delay into account, then the plot is, I would say, much better, isn't it? Much better. For example, at this time, over this region and this region, the spreading has been reduced, and in the end, they are very well separated. You can see a very beautiful two spikes, and so on. And if you compare with the previous synchro squeezing, you see the spike is 250, which is still a bit sprayed, but here it goes up to 400, which is much more concentrated. That is the impact of using more phase information, take more phase information into account. And this is a comparison of the second order synchro squeezing and ideal time frequency representation. So that gives you quite a lot of good information about the dynamics. Then you may ask, well, it seems that, well, you have kind of handled or bypassed the Heisenberg uncertainty principle, isn't it? Is it? The answer is no, certainly not. So synchro squeezing and its variations actually only works on a very spatial subset of functions that you can consider. is not generic at all. It's not generic at all. It needs to satisfy some conditions. Okay, so we obtain the sharpness by sacrificing generality. That is the usual principle. We are not able to bypass the Heisenberg uncertainty principle at this moment. We do not know too much. Maybe we are able to achieve something, but not right. Okay, and this is another example, which showing that we do not really resolve the Heisenberg uncertainty principle. No, we don't. So look at this signal, right? The signal is generated by this guy, and we focus on the complex form, okay, to simplify the discussion. Now, and I only plot you the real part. Amplitude is fixed, but the frequency oscillates with very fast, very instantaneous frequency. Fast, slow, and so on. And this is the power spectrum. Very pretty, isn't it? You can say, there are many spikes. We have multiple components, but well, good luck, right? Now, this is the result. You see, this is the synchronous squeezing transform, which you may say, hey, it looks very nice, isn't it? It's very concentrated, and what's wrong with it? Yes, it is wrong in the following sense. Over this region, in particular, when the cosine function achieves the maximum or the minimum, okay? You can see the red line is the ground truth. The red line is the ground truth, but the concentrated curve or the squeezed curve is somehow a bit underestimated. It's underestimated. In this sense, the instantaneous frequency cannot be fully recovered. We get something wrong. And this something wrong comes from the fact that the phase changes too fast, or instantaneous frequency changes too fast here. So fast that even the second order synchronous squeezing cannot correct it. And so we need to use more phase information to correct it, and that is something we will discuss in the later part of the lecture. And we need to use more information. Okay, and what about the spectrogram? Maybe synchronous squeezing is wrong because you use the phase in the wrong way. So what about spectrogram? Okay, well, looks good, isn't it? And if you say, hey, I superimpose the ground truth, it looks quite nice, isn't it? It seems to superimpose. But it is hard for me, right, to visualize where is the maximum or where is the local maximum because of the display purpose. So now let me help you. I superimpose the local maximum at each time in the frequency axis, the local maximum, which is the purple curve. Now you see the purple curve also has this underestimated issue, which means the magnitude of spectrogram cannot really help you directly. It also gives you the wrong information. So we fail. We need to do more. The third part of the properties of synchronous squeezing is the reconstruction or decomposition. So the condition is like before. Suppose F is adaptive harmonic, satisfies the adaptive harmonic model, and you have separation. Suppose when we have more than one intrinsic mode type function, then we can define a new function, which is F tilde LC at each time, and this time is defined in the following way. We do some integration over for synchronous squeezing over a band at time t over a band, and this band is LO's band, and this LO's band comes from the instantaneous frequency minus epsilon 1 cubic, and the instantaneous frequency plus 1 cubic. So this is a band around the instantaneous frequency, and you do the integration, do some normalization. If you do so, then we have the following fact. That is, the F tilde CLO is actually 1/2 of ALT exponential I 2 pi phi LT plus order of epsilon. What does it tell you? What does it tell you? It tells you that, hey, we obtain the complex form of each intrinsic mode type function in a real form. Remember when we define adaptive harmonic model, actually intrinsic multi function is written in the real form. It's cosine. But right now what we get is exponential. And what is the benefit of obtaining this exponential form or complex form? The immediate benefit is we are able to use this complex form to recover the amplitude modulation and the phase. So we can take an immediate look at this example. Again, this is harmonic function, very simple one. And if you do some integration of synchronous squeezing over a small range, and this epsilon, well, maybe I shouldn't use epsilon because this epsilon is looks like the epsilon in the adaptive harmonic model. This is maybe epsilon prime. It is greater than alpha of support G. Then you just plug in everything. You know how to calculate this synchronous squeezing of this good function. Then you just plug it, and that is what you have. You get 1/2 a exponential I minus 2 pi t c0, and you just divide h0 on the left hand side, and on the right hand side, this is assumed to be 1 by assumption. So you get the reconstruction, which in some sense you can say, this seems to be related to Hilbert transform, right? Because Hilbert transform helped us to get sine function from cosine function in some sense. And we'll come back to this when we discuss Hilbert transform next week, and so on. And this is the numerical implementation, which is actually very simple. You just do whatever we discussed before by the direct discretization. For example, at time, you do the discretization by the uniform grid delta t, and in the frequency axis, you have discretization with the grid delta c, and you have the summation of q over b, and this b is around the LO's IMT function's instantaneous frequency. That is what you have, and this is nothing but a Riemann sum. It's a very simple numerical implementation. Direct discretization. Why? Because everything we do here is are kernels. We only do kernels, so immediate discretizations will be simple. And then we have this time-varying bandpass filter properties that we can understand it from a signal processing perspective, because the reconstruction is surrounding a band, and this band looks like this guy. Okay, the purple dash curve, and so on. And it is a band around instantaneous frequency, which we suppose we know it, but in practice we don't. So we will come back to discuss how to estimate the instantaneous frequency from time frequency representation. So in the end, this can be viewed as a time-varying bandpass filter, because at each time, the band changes. So this is in parallel to the bandpass filter in signal processing. And this is the result. You get a decomposition. The black one in the background is the ground truth. The purple one is a reconstruction. So you can see in the end, this part, the reconstruction is slightly worse because of the very close to instantaneous frequency and so on. But overall, it performs relatively well. And we can also consider or compare it with the global bandpass filter, which in general may not work as we expect. This is a power spectrum. Then what will be the band we choose? It's hard to say, right? But then we say, hey, let me do you a favor. You see, for this component, it is around 4 Hz to 8 Hz. So let's just focus on 4 to 8 Hz roughly. And then this is what you get, the red one, which is, well, difficult for me to interpret. You get a very strong interference. So the fourth property is the robustness to noise. So again, we have the same condition. So the theorem is the following. Suppose the noise is of standard deviation sigma greater than or equal to 0. Okay, then what it means is the noise at each time, if you can realize it or understand it, it has standard deviation, which may be positive or or which may be possible, or even 0. Then when it's 0, there's no noise, right? And you fix some gamma. Then synchronous squeezing transform of the noisy data at time t and the frequency c will be equivalent to SF plus some error of order epsilon, which comes from approximation, and this gamma sigma comes from noise with high probability, where the probability is greater than 1 minus gamma minus 2. So this theory, actually, if I want to give you the full version, we need to be very careful, because in a continuous setup, the noise, what do we mean by white noise? Usually you have to write it in the sense of distribution. So if you have interest to fully understand what's the meaning here, you have to go to the paper. You need to consider this a generalized random process and how it works with the testing function, so that you can get a noise, and the noise actually can also depends on time. But to simplify the discussion here, I give you a very simple version of the theory. Okay, now let's see a noise example later. So this is a very simple case. We have the clean data, and this is a noisy signal, which is contaminated by very simple Gaussian noise. This is the synchronous squeezing transform. You can see it's quite similar, isn't it? There are some background strange stripes, but overall it looks okay, not terrible. This is robustness result. It's a pointwise and so on. And this is second order synchronous squeezing. And the second order synchronous squeezing, you can see there are some curves which seems to be more dominant, and those curves are more difficult to really analyze. At least we do not know the analysis results, or we don't know too much features of those bands or how these behave. But we know more for first order synchronous squeezing, which we'll discuss in a bit about the distribution. But second order is still an open problem. We also have robustness of short-time Fourier transform, because in the end of the day, short-time Fourier transform is nothing but you kind of doing some local averaging of noise. So you see, this background has some weird stuff, but overall it's okay. The fifth part, or the last part of the property we want to discuss today is synchronous squeezing is less dependent on the window. Or we can say it is more adaptive to the signal. In the following sense, again with the same condition, then in the reassignment rule, well, you see, the so-called error actually is of order epsilon. And this order epsilon, what is the hidden constant? We haven't discussed it. The hidden constant will depend on the moments, absolute moments of the window. Absolute moments of the window. In the reconstruction theorem, I told you, this order epsilon also depends on absolute moments of the window you choose. In this sense, you can choose many different windows. As long as their absolute moments are similar, in particular, we only care about the first three order absolute moments, then we get similar results. That is, in this sense, the independence of the window, or less dependent on the window, or adaptive to the signal. So let's take a look at this example. Three components: the clean signal, the ideal time frequency representation, and I give you three different windows: Gaussian long, Gaussian short, and the Blackman window. Then this is a short-time Fourier transform, and this is a synchronous squeezing transform. As you can see, they look more similar compared with the spectrum, right? More similar. Although they are still have some difference, which you can tell, right? There's still some difference you can tell, but the difference is less dramatic compared with the short-time Fourier